So do you remember a long time ago, first lecture of the whole term, we talked about statements and how they're not allowed to use variables, right? Because if you have some variable in a statement, well, then it will, sometimes it makes the thing ambiguous, right? So remember, if I write just x bigger than 0 or something is not a statement because its truth value depends on what x is. So now what we're going to do is give a meaning to these kinds of not things which are not statements. We're going to call these open statements. So I'll say this is not a statement, but it is an open statement. So formally, an open statement is an assertion by which so when I say assertion, I basically I mean just a sentence, which kind of can be true or false in a way, but so which depends on one or more variables. So you can actually think of open statements as being like functions, right? If I write we'll often write open statements with, in function notation, like p of x. So p of x is an open statement where the variable is x. And one example is, maybe I'll just use the same example again, right? The statement that x is bigger than 0. So px, this doesn't have a well-defined truth value. It doesn't have the same truth value for every x. So if let's say I take p of 3, I would say that's true, but p of -10 is false. Is that sort of clear? One weird thing about one of these open statements is, okay, this makes sense. If I plug in numbers, if I plug in 3 for x, that makes sense. If I plug in -10 for x, that makes sense. But this only makes sense if you plug in a number, right? If I plug in, if I plug in dog, p of dog makes no sense, right? So, that sounds silly, but it's actually kind of important that when you have an open statement, you need to sort of specify the universe of possible choices for the variable x, okay, in order to make it make sense. So the so-called universe of an open statement px is the set of possible values that you can substitute in for x. Actually, if you do think about an open statement as being like a function, what this really means is that the universe is the domain of the function. But we haven't really formally built up those definitions yet. But if you already know what the domain of a function is, then this makes sense. But because we haven't formally defined functions and we haven't even really formally defined sets, we're just going to call it the universe. But later, it'll kind of become more formal. So here's a kind of key thing. All of these things we learned about laws of logic and things like that, those all apply the same way to open statements as they do to statements. So for example, if I take px implies q of x, for example, we've got the contrapositive thing that not q of x implies not p of x, right? That these two things are logically equivalent, for example. And all of the other things we built up, all of them apply in the same way. Obviously, if this was the end of the story, it would be kind of boring, right? Because what's the difference between open statements and general statements? So the difference comes in when you involve something called quantifiers. So often in mathematics, you often have these kind of open statements that depend on a variable, and you want to say that they hold for every choice of variable, or that there exists a choice of variable for which they hold, right? That's usually the type of things we're saying. For all x it is the case that something happens, or there exists an X such that something happens. So let's introduce some notation. So if I put an upside down A means for all, a backwards E means there exists. So for example, what I can write using this is, so an example, so suppose the universe, so this is how these kind of things will usually start. They start by specifying the universe. Suppose the universe is the set of all positive integers for each n in the universe. Let Pn be the statement that n is prime and n plus 2 is prime. So from this, I can write down. So okay, so here I'm saying let Pn be the statement. Notice I'm not saying open statement. Sort of for each individual n, Pn is a statement. But if you think of Pn as a function depending on n, it's an open statement, right? Okay, so I can write two statements. So I can write for all n, Pn. So this is a statement. So is there exists n, Pn. Okay. The meaning of these statements are that, so the first statement says that for every n, Pn is true, right? So when you write for all n, comma, Pn, so that's like saying P1 is true, and P2 is true, and P3 is true. So actually, you can write this as a big and. So it's kind of P1 and P2, and dot, dot, dots all the way to infinity. So that's the same as for all n, Pn. If I write there exists n, Pn, that's saying that there exists at least one n for which Pn is true. So this is the same as P1 or P2 or P3 or dot, dot, dot onto infinity, right? So that's the same as that. That's the same as that. Are either of these true? When I say either of these, I mean the statement for all nPn or the statement there exists nPn. Is the first one true? Seems very false, right? So why is the first one false? Yeah, certainly not all numbers are prime. So, right, so this one's false. So to show it's false, all you need is one counterexample, right? So for example, if I take P2, so if I can say because, let's say P2 is false. Because even though, or maybe I'll say P4 is false, right? That's even super false because 4 is not a prime number and neither is 6. It's very false. What about the second one? There exists n such that Pn is true. Okay, so some nodding of the heads. Looks true, right? What's a reason it's true? Yeah, totally. So it just needs to be, it's a big or. So it only needs to be true once. And so P3, so it's true because it's an or. And if I look at P3, P3 is true, for example. Okay, so that's how these quantifiers work. You have for all, and you have there exists. Okay. For all, you should think of it as a big and, that it has to be true for every different thing in the universe. And there exists, you should think as a big or, that it has to be true for at least one thing in the universe. So where things start getting complicated is when you have a whole bunch of quantifiers back to, you might have many variables, right? And you can have a quantifier for every variable, which, you have some for all, some for there exists, and that can become pretty confusing. Okay, let's see an example of that. Well, actually, maybe before we see something with more than one quantifier, maybe I'll just do one more example with just one variable. So, but this time I'll have two different statements. So let the universe be the set of real numbers, and so let P of x be the statement that x squared minus 5x plus 6 is 0. I'm going to let Q of x be the statement that x squared plus 1 is 0. And I'm going to let, let's say, R of x be the statement x equals 3. Okay? So let's try to work out the truth value of these statements. So there exists x px. Secondly, for all x px. Third, there exists x qx. And let's throw in some other examples. So there exists x comma px and rx. Right? So we can kind of take compound open statements, right? You can use logical connectives. And how about for all x, rx implies px? So we could see we're getting things are getting a little bit more complicated. And let's say for all x, qx implies rx. Okay, lots of examples here. So to be clear, P of x, Q of x, and R of x are not statements. They are open statements. But when I put quantifiers with them in this way, these 6 things are statements. These have an unambiguous truth value. Each of them has a truth value, right? P of x doesn't have a truth value because it depends on x, but there exists x px does have a truth value, right? All of these things have truth values. What's the truth value of the first statement? Yeah. How come? Exactly. Yeah. Now, we should be very careful, right? The universe here is, in all of these questions, the universe is important, right? But this is a very big universe. It contains all the real numbers. There does exist an x such that this is true because, for example, if I take x equals 2, right? If I take, if you plug in a 2, does 2 work? Yeah, 2 works, right? 4 minus 10 plus 6 is 0, right? So this one is true. So true. And the reason is you could, for example, take x because P of 2 is true. Right? That's kind of my reason. How about the second one? For all x, px. Yeah, very false, right? Because P of 0, for example, is false. Right? And this for all means that it has to be true for every choice of x. But here's a choice. If I choose x equals 0, that's a choice for which is false, right? How about there exists x qx? Okay, I see some shaking heads. But yeah, does anyone have an answer? Why is this one false? Yeah. Yeah. Well, actually, yeah. What could be an answer if we had a bigger universe? Right. So if you know about complex numbers, yeah. If you know about complex numbers, you could have x equals I, but that's not in our universe. So that's a perfect answer. So this is false because x squared plus 1 has no real roots. Right? But as it was said, if I let the universe be the set of complex numbers, then it would be true. Right? That's important. Okay. Any questions about any of these? Okay, how about 4? Does there exist an x such that they're both true? Yeah.
Wouldn't you only have to 3 for that, for R?
Totally. Yeah. Yeah, that's a very good point. So here, because, I mean, this is a very restricted statement, right? This is only true when x is 3. So in order to make this side true, x has to be 3, right? And then you think about what happens if I plug in 3 here. You get 9 minus 15 plus 6. It is actually 0. 3 is a root of that equation. So this one turns out to be true. Because P of 3 is true and R of 3 is true. But exactly, you only had to check one value to know the answer to this. Okay, this is an interesting one. Is it true that for all x, R of x implies P of x? Yeah. Yeah. That's true. Yeah. Because remember, with an implication, yeah, exactly. If the first part is false, then the implication is true. So right, again, you kind of only have to check the case x equals 3, and they're both true in that case. Right, so this is true because R of x is false whenever x is not equal to 3 and R3 and P3 are both true. Okay, good. So this is true for every choice of x. What about the last one? For all x, Q of x implies R of x. Looks good? Yeah, and this one's again true. And this was actually kind of easier than the previous one, right? This is true because Q of x is always false. Okay, but again, if I let my universe be bigger to contain all the complex numbers, I could make Q of x true and R of x false. So then it would change the truth value. Okay, any questions about these? All right. Let's look at statements with multiple quantifiers. So right, so here's an important thing. If you have some statement with multiple quantifiers, remember quantifiers are like there exists or for all symbols. So quantifiers are read, well, so they're kind of they're applied in order, kind of left to right. And the order is important. So let's say I let the universe, for an example, equals, again, the set of all real numbers. By the way, I mean, maybe a bit of terminology or notation. This is going to come up later again, but yeah, maybe it makes sense for us to just set this up now. So R is the set of real numbers. N is the set 1, 2, 3, or in other words, positive integers. Z is a set of all integers. So if I say that the universe is R, written like this, then I mean the universe is the set of all real numbers. You know, if the universe is, yeah, so, right, so z is like all positive or negative integers, just, you know, whole numbers, basically. Okay. So if I say, like, the universe is n, then I mean positive integers and so on. Okay, so if I write for all x, there exists y such that, so x plus y is 0, where, again, the universe is the set of all real numbers. Can anyone tell me if this is true? Right. Okay, so indeed, it is true. For every x, there is some y such that they add up to 0, because you would just take y equals negative x, right? But, so this is true. But if I wrote this in the wrong order, so if I wrote there exists y such that for all x, x plus y equals 0, this is going to be false. Right? And all I did was I switched the order of the quantifiers, but that completely changes the statement. Because it's definitely not true that there's some magical number y such that for every x, when I add x to y, it gives me 0, right? That's not true. There's no such y. Is that clear? Okay. So let's think about how to negate statements that have quantifiers. So I guess my question is, what is the negation of, let's say, for all x, px? So here I'm meaning, you know, in general, right? Because I haven't told you what px is. I haven't told you the universe. I don't really care what the universe is. I don't even care what px is. In general, you can think of what is the negation of this. I mean, if you want, you can think of a specific example and think of what would the negation be of that. So for all x, x squared is at least 0, for example. What would be the negation of that? Yeah.
There exists an x where not, like x squared doesn't equal, or isn't greater than 0.
Exactly. Yeah. Perfect. So the negation is that there exists an x such that x squared is negative. Right? Because that's kind of the opposite of the for all statement, right? If I say for all x, something happens, well, the negation should be false whenever that's true and true whenever that's false, right? So the negation should be the opposite. So the opposite of saying that the square is always non-negative is saying that sometimes it's not non-negative, right? This is like saying the square of x is always non-negative, and this is saying sometimes the square of x is negative. That's the opposite of the for all statement, right? Actually, you can think of this in terms of De Morgan's laws, right? If I have some big and, like, you know, P1 and, okay, let's say, for example, P1 and P2 dot, 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 forever. If I negate that, De Morgan tells me that that should be the same as negating each individual thing and putting ors between them, right? So it's like not P1 or not P2 or dot, dot, dot by De Morgan, right? But this is the statement, like this is negating the statement for all x px, and the negation is there exists x not px, right? It's really just De Morgan's law that we've seen before, except it's being applied for a big and with many, many statements in it, maybe infinitely many, but it gives you a big or with maybe infinitely many statements. But it's the same rule. So in general, the negation of for all x px is there exists x not px. Is that clear? So this is the answer to this question. Okay, so what is the negation of, what if I start with there exists x px and I negate it? So there exists x px and then take the negation. Almost. So just one thing I would change in that sentence. So negation of there exists x px. So your suggestion was there exists x not px, right? I would change one character from that statement. But anyone have an idea? Yep. Exactly, yeah. So when you negate these things, you switch the there exists to for all, and you change your open statement to the negation of the open statement. And this is, again, following the same principle, right? It's basically like a big De Morgan's law. You know, you can think of this as a big or with many things in it. And when I negate an or, I get an and where I negate all the little statements in it. So, yeah. Okay. Any questions? Okay. Again, everything gets more complicated when you have more quantifiers. So let's go with, let's say, negation of for all x, there exists y, pxy. I think, yeah, we're going to get really bored of this really quick. Maybe we're really bored of this already. But yeah, what's the negation of this? Yeah. Backwards e, yeah, there exists. Yeah.
There exists for all.
And with y, right? Like, yeah.
And then not.
I agree. Yeah, I agree with that. You can actually think of that by sort of, actually you can sort of use the things we've already developed here with the, with one variable, and you kind of apply that twice, right? So just to kind of do that in two steps, like if I take the negation of for all x, there exists y, pxy. You can think of this as sort of like kind of two steps, right? You can think of this as for all. I mean, you can think basically what I'm saying is if I pick a choice for x, you can think of this as being an open statement that depends on y. So basically, what you should get is there exists x such that, or sorry, anyway, not there exists y. I might just be making it more confusing now, but all I'm doing here is applying my rule here. If you have a for all and you negate it, it turns to there exists, and then you negate the thing inside. And then if I apply the second rule, that when you negate it, there exists, you get a for all, and you negate the thing inside. Then you get there exists x for all y, not pxy. Okay. But if you prefer to just like remember the rule is when you negate some kind of statements with lots of different quantifiers, what you do is you go through them one by one. You change the for all to there exists. So that becomes there exists. This exists becomes a for all, and then you negate the thing inside. So the pxy becomes not pxy, and that's going to work.